Have you ever wondered how to create realistic and detailed 3D models of objects and scenes from images or Scratch? Or how to simulate physical phenomena on a 3D mesh, such as deformation or fracture? If you have, you're in luck, because in this video, we'll tell you about a new approach that can do all these things. This approach is called Flexi Cubes, and Nvidia introduced it in a recent paper published at SIGGRAPH 2023. What is Flexi Cubes? Flexi Cubes is a method for representing and extracting 3D meshes as an isosurface of a scalar field. A scalar field is a function that assigns a numerical value to every point in space. For example, a gas's temperature or density can be represented as scalar fields. An isosurface is a surface that contains all the points that have the same value in the scalar field. For example, the boundary of a solid object can be represented as an isosurface of a density field. We can describe complex shapes simply and compactly using scalar fields and isosurfaces. Some scalar fields and isosurfaces are not suitable for high-quality mesh generation. A mesh is a collection of vertices, edges, and faces that define a 3D object's shape and appearance. A high-quality mesh should have smoothness, accuracy, feature preservation, adaptivity, and robustness. These depend on the geometry and connectivity of the mesh elements. Geometry is the position and orientation of the vertices and faces, while connectivity shows how they are linked. We need an algorithm to determine the geometry and connectivity of the mesh elements from a scalar field. Many existing algorithms exist, such as MC, DC, DMC, and NDC. However, these algorithms are limited to gradient-based optimization. Gradient-based optimization is a technique that improves a mesh by adjusting its parameters according to some objective function. For example, we can define an objective function that measures how well the mesh matches the images to reconstruct a scene from images. Then we can use gradient descent or other methods to update the mesh parameters until we reach a minimum of the objective function. Gradient-based optimization is used in applications such as photogrammetry, generative modeling, inverse physics, and more. However, to use gradient-based optimization effectively, we need two things. First, we need to compute the gradient of the objective function for the mesh parameters. Second, we need enough degrees of freedom in the mesh parameters to represent high-quality, feature-preserving meshes. Existing algorithms for mesh extraction do not satisfy these requirements. For example, MC and DC do not have well-defined gradients concerning the scalar field values. This means we cannot use automatic differentiation to compute the gradients effectively and accurately. Moreover, MC and DC have fixed connectivity patterns that do not adapt to the scalar field shape features or resolution. This means we cannot control the mesh's quality or complexity locally. On the other hand, DMC and NDC have well-defined gradients to the scalar field values. However, they still have fixed connectivity patterns that do not adapt to the shape features or the resolution of the scalar field. Moreover, they have limited degrees of freedom in adjusting the geometry of the mesh elements. For example, DMC only allows moving vertices along one axis per cell, and DC only allows moving vertices along two axes per cell. This means we cannot precisely fit the mesh geometry to curved or sharp features. To overcome these limitations, Nvidia introduced Flexi Cubes, a flexible isotope extraction method for gradient-based mesh optimization for geometric, visual, or physical objectives. Flexi Cubes introduces additional carefully chosen parameters into the representation that allow local, flexible adjustments to the geometry and the connectivity of the extracted mesh elements. When optimizing for a downstream task, these parameters and the underlying scalar field are updated via automatic differentiation. Flexi Cubes is based on DMC for improved topological properties, but extends with two key features. First, it allows moving vertices along 3 axes per cell instead of 1, and second, it allows changes to the connectivity pattern of the mesh elements within each cell instead of using a fixed pattern. These features enable Flexi Cubes to generate high-quality meshes that can fit surface features and find a high-quality mesh with a small number of elements. How does Flexi Cubes work? Flexi Cubes divides the scalar field into a regular grid of cubic cells. Each cell has 8 corners, each with a scalar value. The isosurface intersects the cell at some points along the edges. These points are called edge vertices. Faces connect the edge vertices to form the mesh elements within the cell. The faces are either triangles or quadrilaterals, depending on the connectivity pattern. Flexi Cubes uses 2 types of parameters to control the geometry and the connectivity of the mesh elements. First, it uses offset parameters to move the edge vertices along the edge. Second, it uses pattern parameters to select the connectivity pattern of the faces. These parameters are stored in a separate tensor from the scalar field values and are optimized together with the scalar field values using gradient-based methods. The offset parameters are defined as fractions between 0 and 1 that indicate how far the edge vertex is along each surface. For example, an offset parameter of 0 means the edge vertex is at the same position as the corner with the lower scalar value. An offset parameter of 1 means that the edge vertex is at the same position as the corner with the higher scalar value. An offset parameter of 0.5 means the edge vertex is at the middle of the edge. By using offset parameters, Flexi Cubes can move the edge vertices along 3 axes per cell instead of 1, as in DMC. The pattern parameters are binary values that indicate which connectivity pattern to use for each cell. Each cell has 256 possible connectivity patterns, depending on how many edge vertices are present and how many faces connect them. However, not all patterns are valid or desirable. Some patterns may create degenerate faces, such as zero-area triangles, or non-manifold edges, such as edges shared by more than 2 faces. Therefore, Flexi Cubes uses a pre-computed lookup table to filter out invalid or undesirable patterns, and only allows selecting from a subset of valid and desirable patterns. By using pattern parameters, Flexi Cubes can change the connectivity pattern of the mesh elements within each cell instead of using a fixed pattern as in DMC. Flexi Cubes needs to define their gradient to the objective function to optimize both the offset and pattern parameters using gradient-based methods. The gradient of the offset parameters is straightforward to compute using automatic differentiation. However, the gradient of the pattern parameters is not well defined, since they're discrete values that cannot be changed continuously. Therefore, Flexi Cubes uses a soft relaxation technique to approximate the gradient of the pattern parameters using continuous values. The soft relaxation technique works by assigning a weight to each possible pattern for each cell. The weight indicates how likely or preferable the pattern is for that cell. The weights are initialized randomly or normalized to sum up to 1 for each cell. Then, Flexi Cubes computes a weighted average of all possible patterns for each cell, using their weights as coefficients. This weighted average is called a soft pattern, and it defines a soft mesh that approximates the hard mesh generated by selecting 1 pattern per cell. The soft mesh can compute the objective function and its gradients to offset parameters and the weights. Then, Flexi Cube updates both the offset parameters and the weights using gradient descent or other methods. The weights are also normalized after each update to ensure they sum up to 1 for each cell. After updating both the offset parameters and the weights, Flexi Cubes generates a hard mesh by selecting 1 pattern per cell according to their weights. This can be done by either choosing the pattern with the highest weight or sampling a pattern according to its weights. The hard mesh is then used as the output for Flexi Cubes for visualization or further processing. Flexi Cubes outperforms existing methods in quality, efficiency, and flexibility in all these applications. Flexi Cubes can produce more realistic and detailed meshes than MC or DC, more smooth and accurate than DMC or NDC, and more adaptive and robust meshes than any other method. Moreover, Flexi Cubes can achieve these results faster and easier than existing methods, since it only requires optimizing a few parameters per cell instead of solving complex systems of equations or performing expensive operations. We hope you found this video informative and interesting. If you did, please give it a thumbs up and share it with your friends. If you have any questions or comments, please leave them below. If you want more videos like this, subscribe to our channel and hit the bell icon to get notified.